this. Thanks whoever requested it. All right. So before I jump to next topic, are there any question about the example and the remark? And hopefully you got some relation with physics now.
Is it like all the operators that correspond to some physical observables, are they all bounded, or are there
No.
some? Okay.
No, that's actually one of the reasons von Neumann was forced to develop the theory of unbounded operator. So most of the operators in quantum field theory are unbounded operator. And if you go back to 100 years past, as I was telling yesterday, then there was barely any theory for unbounded operators. There was some, but not very systematic way. So it was literally the development of quantum mechanics that forced mathematicians to develop theory of unbounded operators.
Right.
So it was physics that told mathematicians, look at this mathematics structure. Any other question? Okay, it doesn't seem right now. So now we will again revisit the example to give you a further intuition for bounded operator or when an operator can be bounded. So now we consider same example, but now we are on a Hilbert space setting. So let f be a function from Rd to K. This is a nice function. Okay, by nice, what I mean is actually measurable. Again, you will say, what is measurable? Yeah, let me explain it later. But for the time being, it's a nice function, just think, which you can do integration differentiation. Okay, and now we define multiplication operator. Remember, on a Hilbert space, we need to define domain of MF to L2. Okay, and since I erased it, maybe it's good point to recall. So yeah, U is a dense subset of a Hilbert space. It means that you take the closure of U, then you get the whole Hilbert space. Or you can say this way, you take any vector on H, let's take H, then there exists a positive epsilon and vector in U, so that this is true. Oh, sorry, the other way around. Epsilon positive, of course. Okay, so there's the meaning. Maybe this is more useful who are not familiar, because we have already the notion of convergence in this setting. And this is more metric language. All right. So now question is, what is domain? Because we haven't mentioned. So now we have to say what is the domain. Let me tell it. So domain of MF is the elements of L2 are dk such that, so to be domain, what we need to know, we must, at least we need that if we multiply by f, this will be also in L2, right? And that's the domain. If u belongs to L2 RD. Okay, maybe I should have actually written domain earlier, but for pedagogical reason I wrote it the other way around. So let me play a bit. Okay, so that's in different color so that we don't mess up. Okay, and the definition is as before. So u maps to MFU. Okay, now we have already worked out this situation, and what does it tell? The operator norm of this is the F infinity norm. That means, but do you know that F infinity norm exists in this setting? What do you think? Yeah, feel free to raise. What do you think? Do you know that the F infinity norm exists in for this function? Or are you lost? Should I explain it before again? Should I explain it? That's what you mean, or you mean that we know that L infinity norm exists? Could you please tell what you mean by yes? Should I explain, or you think L infinity norm exists? Which one? Okay, good. Good, thank you. So by this condition, we do not know whether L infinity norm exists. Yeah, because why? Just give you an example. So take F, for instance, 1. Okay, we take an example. So F is 1. Then the L infinity norm will be infinite, right? Because you are integrating over or taking the infimum over all f of x. So there is always a x, and then you can get in. That means this condition is not sufficient to stop it. Is not sufficient to stop it. Okay. In other words, MF is bounded if and only if f belongs to L infinity or dk. Okay, and now come back to your question or partial answer. For a position operator, if the position operator is in L infinity, then it is a bounded function, a bounded operator, otherwise not. And later we will see that in general position operator is not L infinity and it will not be a bounded operator. And that's one example what forces us to consider unbounded operator. And we will spend most of our lecture with unbounded operators. But hopefully you get a glimpse how condition on this multiplication function actually tells that whether it is bounded or unbounded. Maybe another thing will be further clarification. So now consider what we have done, but instead of R, we consider a compact set. This is compact. Then this is automatically finite. So compact, if you are not familiar, think like a circle. Okay. So if you are a circle, then you don't have chance to go infinity, right? You will always somehow bound it. And then this tells that MF from domain MF in the sense that maybe I made a bit color so that it more easier to follow. Okay. Compact. So now instead of RD, we consider from K. And this is also K. So this to so this blue MF, which means we are from K to L2 K blackboard K. This is always bounded. Because why? Because of this compactness. So I give you some time to contemplate. Let's give you 2 minutes. Yeah. So that's one very concrete example. Take your time. Ask any question you have. Even if this is question I don't understand anything, explain from begin. Please go ahead.
Can we prove it by a contradiction approach that an operator is bounded or unbounded?
Sometimes yes, sometimes not. Because contradiction, to apply contradiction, you usually need some more information so that you can go on with contradiction argument and you can contradict. So this is not always possible. So it depends on the situation. In principle, there is no problem. Yeah.
So an bounded operator is always a bounded operator, or maybe it can.
No, again, bounded operator means you have to say what's the domain first, because as you see, when the domain is this one, then it's always bounded. But when the domain is this one, then it is bounded under this condition. So when you are considering operators on Hilbert space, please concern about this guy. So this guy says a lot about what is going to happen, and that's why I use a very lengthy example at the first lecture to introduce you why domain is important. Because without domain matching, remember, we cannot take powers on an operator. Now you see, even whether, so we have seen that if it is a bounded operator, then it's nice. There are algebra, you can take power and everyone, nice things. But whether this is a bounded operator or not, that itself depends on the domain. So operators on Hilbert space, one of the fundamental notion is that domain. And it makes sense because what is domain? If you think about a function, domain is the starting point which you apply to a function and then function tells something. So for a function, usually if you put something very weird and if function is nice enough, then nothing very exceptional happened. But for operator, they are wilder object than a functions. So they are more sensitive, don't take in a literal sense, to domain than usual functions. That's why you see the domain dependence is very severe here. For one domain, this may or may not be bounded. For another domain, it will always be bounded.
So if we change the space, so the domain will change or it will remain the same?
No, it may not remain the same. Of course, domain will change, and it may change such a way that it is bounded. It may also not be bounded. And we will give some concrete example, hopefully end of today, or if not, then next lecture. That if you change, so let's you change this space. Okay, we already have an example here. So if you change this space from L to RD to L to K, then you see the domain changes, and it changes such a way that is bounded. And you can say, okay, still we are L2. How about we change L2 to some other vector Hilbert space? That we will do. And then we'll see that sometimes it has a completely different situation. And that's something very important in quantum mechanics. For instance, the Dirac bracket notation, this is hidden in the domain issue that usually not addressed in usual physics book, and we will discuss in detail. So you are right, it changes, but it will, the way it changes is not clear. Like if you change the domain, it will always be bounded. No, it may or may not be. Even you can change the domain in such a way, the notion of boundedness is not applicable. Because you can consider, instead of a Hilbert space, some normed space. And we will introduce some space which is even more general than this. And then notion of boundedness exists, but you will see that that bounded and this bounded are not always coincide. So you are right, is domain, is this space, both are important. And since we have considered dense domain, so that's why when I call domain, kind of the ambient space is automatically implied, yeah, because we have considered dense domain. What is the measure RD? Is the canonical measure. That's why I am not writing the measure, but at some point I will talk shortly about measure theory, and then I will mention the measure. So we will use the standard Lebesgue measure on RD. Okay, I'm confused between compact and compactness are the same. Yes, so compactness is the property or adjective, and compact is the thing. Domain in function sense. I mean, domain in the. Sorry, go on.
Completeness. So completeness also means that the limit is also present in that space, and compact also means that the limit is the function is converging, and the limit is also present in that space. So are they same? The compactness and the completeness.
Oh, no, not same. So compact means every sequence has a converging subsequence. That's compactness. And completeness means for every element of a vector, you have a sequence of vector that converges to vector. So both are not same.
Can you go again?
So okay, maybe I write. So compact. So compact space. Okay, compact space. Because later we'll see there is something called compact operators. Loosely speaking, every sequence has convergent subsequence. Right, sick. Okay, that's compactness. And completeness means every vector. Okay, so there exists sequence that converges for each vector. Okay. Sorry, I misread actually. Thanks for your question. It's compact and complete. Is it clear? Again, if it not, keep going. I want to spend, if necessary, rest of today's lecture only to explain this. But this is really one of the heart of the functional analytics setting for operators. So please take your time, ask as many questions as you wish. So I don't want to cover lots of things, but you don't understand. Later I will prefer I cover only one topic, but you understand clearly. You take any sequence, in particular Cauchy sequence, because we are considered complete inner product space, and as we defined, complete means in the sense of Cauchy sequence. Does it answer your question? Okay, thanks. Yes, exactly. So maybe sometimes for functions we have this picture, right? So f is a function between a and b, and domain is the subset. Actually, from here it gives to the image. So for the usual case, any subset is good enough. In this case, we are considering dense subspace. That means if you take any vector, there exists at least one vector here. So this is arbitrary close approximation of this vector. Because you can think this way. So what is one? One is that you take any x, and then you take a number. So okay, let's go there. Where is the definition? Yeah. So in this case, the whole thing is x. Now, since x can move in Rd, or say R, that means x can go to infinity, right? And so it's just infinite. So you can think like, what is the maximum thing can happen? And then norm is something, the maximum happened and then something related with the maximality. But if it is, since it's unbounded, x can move in an unbounded situation, it can escape to infinity. Yeah. So just think this thing, but instead of f of x, just x. And now x can definitely be infinity, right? And then it can be greater, less than infinity. So yeah, what we are here, and then for operators, we have similar situation, but now we have a dense domain, and we will come to what is image. Is it like integrate? Kind of. It's a generalization of integrate, not a generalization. It's like a, yeah, let's take P norm, because infinity norm is a bit complicated, but if we take P norm, then it's literal integration. Yeah. So let's consider this one, okay? Because this is also true for this one, because this is infimum is hard to visualize. So what will happen in this case? Everything is one, right? So I didn't forget to write dx. So maybe I write naive way. In this situation, this is x. Now, if we integrate over Rx, then what will you get? You get infinity, right? And infimum norm is when the power is also raised to infinity. So it's another way to intuitively visualize. So that is the answer to your question, or should I explain more? Or any further questions? Okay, pleasure. But yeah, it would be nice if we do some homework like computing infimum and supremum. But yeah, it unfortunately requires quite a bit of background and we don't have that much time.
How we can define the intrinsic property of an operator? This property is not changing when we go
There is
downstream.
no way to define operator on a Hilbert space without doing the domain. So in a way, by an operator, we mean a mapping. Where does a mapping? And if it is a Hilbert space, let's put this way, domain of T. So if you really want to write in a very, say, detailed way, then when we mean by an operator, we have to write like a at least triplet. The mapping, its domain, and the ambient space. So that's three data you are required, and then you can, of course, study. But there are intrinsic things we can study. For instance, the spectrum of an operator. This is an intrinsic thing, and we will study it in the context of harmonic oscillator. I mean, I will discuss a bit about general situation, but not very detailed. But we will solve the spectrum of harmonic oscillator, and then you see that, for instance, how the operator space, spectrum, eigenvalues interact. So there is no notion of an, say, operator. I mean, in fact, I mean, even before going intrinsic thing, without domain, you cannot actually define an operator, because that's another thing this example shows. When you change domain, your operator also changes. So it's not like operator is an object and domain is a kind of label. No, operator means an object, it requires domain. Without domain, you cannot define. If it is a bounded operator, then the domain is everything. For instance, in this case, this is good, or this is sufficient. You don't need to consider, because it's a bounded operator. However, in this case, this is not true, because this is bounded or not bounded depending on f. So if f is in L infinity, then you can define it on whole L2. But if not, then you cannot. And the reason is specifically here, because if it is not L infinity, then this cannot be satisfied. So then your domain might be void. There is nothing. Yeah. So an operator means operator with its domain. And that's
Can
yeah.
we apply some sort of constraints on an operator?
Constraints. Could you?
Means we want the like some sort of behavior.
Yeah, sure. We shall do it. So we will, for instance, use mostly self-adjoint operator, which is super important or fundamental in quantum mechanics, and that will constrain the operator and its domain, and we will see how it constrains its domain. We will also study compact operator, that is also a constraint, like trace class operator, we will consider, and then it will be another constraint. So at least we will study trace class operator, self-adjoint operator, and what? And maybe something in between a bit. But these two we will use and explain more and less detail, because these are super important in quantum mechanics and some other applications. And then you will see how it constrains the domain, and overall how it constrains the operator. In some sense, this is also a constraint, right? So you say, if MF is a bounded operator, then this is a constraint. Or we can say other way, if this is true, only then MF is unbounded bounded operator. So that's also a constraint.
But the sequence also applies some sort of constraint on the operator, on an operator or not.
Yes, we will come to unbounded case situation, because what we are happening now, since these are bounded operators, so they converges. So what sequence is doing now here like this? So let's take a sequence, say U1 or UN. And this converges to U, because it's dense, then when it converges to U. Okay. Now, an operator acting on UN, question, does it converges? For bounded operator, it does. For unbounded operator, it does not. So since it does, we are not delving much in the sequence part now. But after next lecture, or maybe after next, we will go to unbounded, and then this will come very explicitly. That's why we are not discussing this now, because of boundedness. But this is coming. Thanks for all the interesting questions. I really appreciate. Please go on. Okay, feel free to raise your voice at any point. It seems we are, say, in a partial saturation stage, that we don't have right now any question. But whenever you have question, raise your voice or write in chat. So let's continue now a bit more into bounded operator. And we need to introduce some tool, which I think part of you are familiar. But anyway, let me introduce. So definition. So let f is a L1 function. Okay. And yeah, always I'm using the standard Lebesgue measure. That's why I'm not writing it. Now, when it's L1 function, we can define its Fourier transform. So let's denote it by hat. Yeah. So Fourier transform is given by two pi d by 2 integration over RD over minus x dot c f of x dx. Since I have written the arguments, let's those argument here. Okay, so I wrote it in a different color because this is a matter of convention. I will not use this one, but if you can use, there is no problem. So there's the Fourier transform. So if any of you are not familiar, then just take, it's like a machine. You take f, and then the hat machine turns f into f hat, which looks like this. At some point, we will explain what is meant by this, maybe 1 or 2 lecture after, but for the time being, if you are not familiar, just think this as an expression. Okay. Now, the question we ask, so let's denote this transformation, this calligraphic f. That means it takes RD, k, an input, but question is that where does it belong? And this belongs to a space which is quite complicated. So if we change this one, then we get actually a nicer property. And that is super important in physics, so let's go there. So let me introduce Proj space. So S for Schwarz, named after French mathematician Laurent Schwarz. So this is all smooth functions. Okay. Such that for all alpha, beta, n naught d, this is true. X alpha, d beta, f. Sorry. No, it's not. Is finite. Now question is, what is D? So this is something called multi-index notation. Again, if you know, then you know. Otherwise, let me introduce now. So what this means is that alpha can be written as alpha 1 dot 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 alpha D. Okay, and same for beta. And D, beta, sometimes there is the convention of minus I. So here, this means alpha 1 dot 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 for D. So it's the usual indexing we sometimes use in Rn, like x1 dot 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 xn, and now it's abstractly alpha. And then d beta dx1 beta 1 dot 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 dxt beta d. Yeah, so this is something called multi-index notation. It's just a convenient one. Then usually we use x1, x2. Okay, and then you know already these norms, so this is a space. So how you can visualize or think about this space? You can think, okay, this is the space where derivative of a function grows slower than some power. Okay, or you can say that this growth is not more than some power function or some polynomial. So you can think like this has at most polynomial growth. Yeah, that's how you should think about this space. Okay, so why we have introduced Schwarz space? Because if U is a Schwarz function, then we can do integration by parts and Fourier transform of dx alpha u. So when we do Fourier transform, it becomes the Fourier variable, which I denote by C. This is I C alpha. Okay, one notation is missing. Let me also introduce here. Oh, no. So this is this, and alpha means alpha 1 multiplied ... alpha d. Yeah. Okay, so this is this alpha, and then Fourier of u and this variable. I think some of you are already familiar. Like if you apply derivative, then in Fourier space it just gives power of Fourier variable, and that is what it is. If you are new, then just take this as a black box. You can prove it. It's not hard. Just you have to do integration by parts. It tells that the effect of differentiation in Fourier space is same as multiplied by the order of differentiation you make as a power of the Fourier variable. That is what it tells. Okay, maybe I write it here so that we have more unified view. Okay, and one more, that you can come back the other way around. So you have Fourier, now power of x, u again. This will be in the Fourier variable, and now you may guess you should get differentiation, and that's what you are going to get. Now, differentiation in the Fourier variable, alpha Fourier of u psi. Okay, and that's really nice. So you can actually come back and forth, right? You can go from this world, and then you can come from this world to this world. And that's one of the nice thing about these Schwarz spaces. So from here we have seen that Fourier transform maps Schwarz space to Schwarz space. But this is not true for L1. See? This is not true for here. So you see why this space is a nice. Okay, now one of famous result in Fourier analysis, this Plancherel theorem, which some of you may are already familiar with. Theorem Plancherel. This tells that, okay, before going, maybe I give one more step. So you can take completion of Schwarz space. That's another nice property. So completion of Schwarz space, and that you give L2. So Schwarz space is a dense subset of L2, yeah, in our language. How it is done, you need to know a bit about completion. Since I haven't discussed it, let's use as a black box. Okay, and now we have our nice result. This tells that Fourier transform now extend. So this is extension. This f and this f are not same. Okay, this f is an extension of this f, but it's customary to use same notation. If you are confused, let me know, then I will use different notation.
I think using different notation might be better.
Okay, sure. So Fourier, what should be the notation? Okay, let me use then this notation. Here. Here I use the hat notation, okay? And now I use f. So this f is an extension of hat on L2. So now Fourier transform don't only map L2 to L2, but this is a unitary map. Now I remember, I forgot to introduce what is a unitary map, but let me introduce. Sorry. Another definition. So T belongs to bounded operators between norm space H and K is an isometry if and only if Tu equals to UH. Or in other words, you can also say the operator norm of T is 1. Okay. Now, okay, I need a few more. Sorry, I should have introduced it earlier. But never then later. Okay, some more definition. Okay, T is bijective if there exists an inverse map, but the inverse map is not necessarily a bounded map. It may or may not. Okay, so I different color. Okay, now make things more clean. H is a norm space. K is another norm space. Now we consider Hilbert space setting. So H is a Hilbert space. K is another Hilbert space. Sorry, I forgot to put H here. Okay. Okay, now T, operator from H to K, is called unitary if this is bijective and isometry between these spaces. Okay. In other words, you can write it as PU PV equals to okay. Good. Now we have all these definitions. Sorry. And one of standard and very important result in Fourier analysis is that Fourier transformation is an unitary operator from L2 to L2. And we will see how important this is, for instance, in quantum mechanics. If we don't have this unitarity, then lots of things in quantum mechanics we would not have been able to do. Okay, so although this is not sometimes explicitly stated, but this is heart of the part of argument used in quantum mechanics. Okay, so maybe I give you some time. Any question in case you are not familiar with this, or even if you are familiar, if you have any question about Fourier?
How the isometry is related
Related to what?
To unitary.
So you see, unitarity already has isometry here, right? Because you can put T this side, then okay, it depends, but okay. You can already see that this can be true when the norm is T norm is square is 1, right? Otherwise, this cannot be true. For instance, if you go this way, so T square U V, that means this norm has to be 1. Otherwise, you cannot satisfy this, right? So that's how isometry enters in the unitarity business. And bijectivity need because we did this change so that you can come from here to there. So we use T inverse actually here. Is it clear?
Yes. Yes.
Thanks. Okay, any further question? Comments? No?
Can you please give me the geometrical interpretation of this space?
Which one? L2 or Schwarz space?
Schwarz.
Schwarz space doesn't have very, or at least I do not know much of geometric information. It's more because it's not Hilbert space, but it's a dense subset. So you don't have a Hilbert space structure on Schwarz space. Where is our Schwarz space? Here. So this is actually something called a topological vector space, and we will discuss about it. And then you will see that there is a notion of norm or distance, and that's where you can think about geometric thing. But we haven't talked about. So this is a something called semi-norms, and since we haven't talked about, so this is an example of that. But since we haven't talked about it yet, can I postpone until maybe 2-3 lectures? Because then we are going to, okay.
Sure.
So then, and if I forgot, please then ask me. So we will discuss something called topological vector space briefly, and then we will see that this and this has a dual, and then you see some geometric picture, this Rees representation theorem and those sort of thing. But the thing we have discussed so far, Hilbert space mostly. This is not a Hilbert space, so we don't have geometry in the Hilbert space sense right now. Thanks. Any other question? Okay, you can ask anytime. So let me now go next example. Okay, so one of the motivating thing we used at the beginning is differential operators or differential equations. And maybe at some point we should, and we asked where we can compose this thing and all this thing, right? So maybe this is the time we address this. So due to this unitarity, I mean, okay, this is not part of example, but what this gives us? This gives us, first of all, so Laplacian, I use the minus convention here, dx square, and this Plancherel theorem tells us Fourier transform of Laplacian of u is psi squared. We have seen this thing here. Here we're using this one. Yeah. Fourier transform of u in L2. L2. So it's exactly same here. Okay. All right. Now observe that. Isn't this a multiplication operator? So who thinks this is not a multiplication operator? Because we can just write it multiplication by c square Fourier transform of u, right? And then it's very nice because we have already studied multiplication operator. So let's go there. So domain of Laplacian is all L2 functions such that we just use this property written up. They are Fourier variable square and hat. Okay, let's not use hat because we're using differentiating to thing. If f belong to, okay, let's not use f here because f is something else. U L2 RT. Okay. Yeah. So that's our domain. And now we can say Laplacian is the operator on L2 to L2 sorry. Forgot to write domain box triangle U maps to U. And how it is defined? This is defined using this way. Okay, is it clear, the definition of Laplacian? In other words, we can say this is the, maybe I write different color so that you don't mess up. Okay, now let's go back to our first example, or second example. We are precisely in this situation, right? So instead of f, we have psi squared. And what was the conclusion? This is bounded operator if it is L infinity. Now let's go back to our setting. Is psi square by any chance L infinity? No, because we have this again infinity issue. So Laplacian is an unbounded operator. So now we have one example of bounded operator, one example of unbounded operator, and how really we compute thing or we understand thing. I hope we have very concrete visualization. I'm sorry, not visualization, working principle. And now again, come back to your question again partially. We have just encountered our first example of unbounded operator, and position operator is also an unbounded operator. And those who have done quantum mechanics, they know this is actually the momentum operator, and momentum operator is also unbounded operator. Now you see how unbounded operator arises in quantum mechanics. And historically, these are the operators that told mathematicians to develop a mathematical theory. So physics came first, there was not mathematical theory, and later mathematicians developed the whole theory of unbounded operators, and that's what we are mostly going to discuss in rest of this lecture. So maybe I use this as a second revised motivation why we need unbounded operators. And I invite you for your questions, comments, or anything, suggestions. And if you are lost, again, feel free. So you think maybe we go for another poll? Today we didn't go for any poll. So please participate in the poll. Let me give some feedback so that I can get how you are feeling with this lecture, what I can do. Okay, I think we got some idea what's going on. Thank you very much. So maybe I use the rest of time today to explain rather than using a new topic. So please ask what should I explain or why should we start, and then I shall try to address all of your questions. So is this lost feeling comes from like all these terminologies are very new and very abstract, something like this? So you are finding it hard?
For me, it is, I've never looked at quantum mechanics through this lens, and I'm not really familiar with this language either, so it feels very unnatural for me.
Okay, very good comment. So may I ask, like, what's your viewpoint or your view towards quantum mechanics? Maybe we try to bridge. So you have encountered position momentum operator, right, in quantum mechanics?
Yes,
Okay, so how you view momentum operator in quantum mechanics?
I just view it as a tool that I operate on the state vectors to get.
Mm-hmm.
Yeah, I've never really thought deeply about where this comes from, I guess.
Okay, so the bridge is like this. These are your state vector. I mean, anyway, we are going to discuss it later, but right, these are the time we should try to connect. So these are your state vectors. Okay. More precisely, these are the pure states of your system, U. Maybe I write to more familiar notation. So this is probably you want to write, right? Okay. And then it gives something. So if you remember in quantum mechanics, you go to momentum space and then position vector, you give you position eigenvalue, something like this. So P hat P equals to P get. Are you familiar with this, or this is something you are familiar?
Yeah.
Yeah. So let's try to connect. So this is loosely speaking. This is U is your P bra, okay, and this P is this eigenvalue square, and it is that. Now question is that how they are really connected. I will request you just give me 2 more lecture. We will have an entire lecture on the bracket formalism in quantum mechanics. So we will discuss how this and this are related and what are these actually. So those who are familiar with this language and those who are not, this is a symbolic thing, right? You say something is bra or ket, but what is mean by a bra? I don't think you have ever seen a definition of bra in quantum mechanics, have you?
No, not really.
Yeah, so we don't really mention what is a bra. We write a symbolic thing and we say that this is something, if you act by this operator without telling what is this operator, then it gives you this. And then we compute and we find interesting results. Am I right?
Yeah.
Yeah. Now, one of the purpose of this course is to reproduce this result, but now telling precisely what is this guy, what is this guy, and what is this guy. And today you see just one glimpse. This guy is this guy, this operator. And what is this? You have to wait to lecture. And this probably we'll discuss next lecture. Okay. Now, already it was asked before, and maybe it's also relevant now. Why this picture, not this picture, or the other way around? So it's a partly matter of taste and matter of what you want to do and what you want to understand. If you are satisfied, like I have some functional equation which gives me kind of a rule of the games, then of course you can go with this because it's a nice thing and you can just compute thing if you know the rule of the games, right? And then there is no problem. And of course, this is a standard trend in physics, and I am no one against it. And it has produced immensely successful history of science. But if you want to understand, no, I definitely am happy with, or I am partially happy with the rule of the games. But I really want to understand how the rule of the games are coming and why these are like this, why not like this. If you want to ask this sort of question, then you need this picture. Okay. Also, hopefully some of you, or maybe all of you, will pursue math, physics, or something relevant professionally at some point. Then also it depends what you want to do professionally. If you want to, say, do some research where this level of precise understanding is important, then you need to know this language. And then you can solve problem where this preciseness is important, or in some sense essential. There are also problems where you don't need this at all, only this is sufficient, and you can also work this sort of problem. Both are important, both are interesting, is depend on your taste. Okay, so I want to merge or make a bridge, maybe say this way, like a bridge. Yeah, hopefully it will look like a bridge. If not, then Okay, let's not try what I cannot draw. Maybe this way. So you have quantum mechanics. That is nature, right? What's happening, or description of nature up to some energy scale. And then there is a mathematical world, or mathematical representation of our universe. So what we do in theoretical physics is we map maybe not, yeah, there. Okay, and then we work here and then come back to here and say, oh, look, these are my prediction, check with experiment. If it matches experiment, then this is right. If it doesn't match with experiment, then this is wrong. Yeah, so around 100 years before, Heisenberg found the right answer of hydrogen spectrum, and that's why we started to appreciate quantum mechanics. Although still there are issues with foundation of quantum mechanics, and people are working on it. If some of you are interested, maybe you will also work on it. And if you are interested in those aspects, then you need this precise mathematical representation of the universe. And if you are not interested in those areas, rather you want to compute using the rules of the game, then you don't need it. Yeah, so it's a matter of taste, matter of wish, and end of the day, yeah, I would say my job is to show you two sides of the bridge, and then you decide what you like for professionally or not. So there is a comment, just a suggestion, since lots of them are not familiar with real analysis, it's very useful if you or TA could dedicate it. Thank you a lot. I will. I am not going to take this TA tutorial because I'm not here next week. I mean, I'm traveling for conference. But I shall definitely tell. So then, let me ask all of you: should I postpone the homework and dedicate it entire tutorial session on basics of real analysis?
Maybe both can be simultaneously.
That will be good, but we have only 2 hours. I mean, real analysis is a whole coursework, and
No,
no one.
I meant you can put the homeworks up for us to do,
Hmm?
but you can also do the real analysis course and we will submit the homeworks after it.
Okay. So I give you homework to submit in 2 weeks, and next week it will be some review of real analysis. Is
Yeah.
that better? Okay. So thanks who have suggested and all of you who responded. Yeah, I really appreciate this sort of thing, like interaction. Let me know what is best for you, because I am here to give you or to support you for your interest. Yeah, not to suffer and not to just say some big words thing. Okay. So yeah, now come back to, so does it gives you some feeling now how these two worlds are related, and what, and you will see more precisely what, I mean, now I am just telling by words, but you will see time to time. So today we just saw the first glimpse, but gradually we will see actually which level this picture can give you better result, which way you want to define better, and which way this is more say useful. You will see. Okay. So there is a whole branch of mathematical physics, and that's the where this letter is important. And then of course there is theoretical physics, where this language is important, and both are important, both are interesting. Again, it's your test. So does it address some of your feeling? Okay, so there is a question that to the quest of understand quantum theory, more precisely quantum field theory from this precise or say mathematical language, has developed new mathematical understanding. And you mentioned some of the things like algebraic structure, Hopf algebra, and then category theoretic viewpoint. And you ask, do you think quantum theory is something for the physicists to take on anymore? Definitely it is. I think end of the day, this is my viewpoint, and I know there are people who will differ. Physics is an experimental subject. Okay? So I think Feynman told you, like, no matter how beautiful is your theory, if it doesn't match with experiment, then it's not correct. So my motivation, or the way I started mathematical physics, and I'm trying to do it, is that this something represents what we know is a right description of nature up to some energy scale. Yeah, it's not just something, a toy model or something which has nothing to do with nature. Not like that. This has a, you will see very precisely how it arises in harmonic oscillator and sort of thing. And I want to understand nature, but I also want to understand each and every aspect of this theory. And that's why I became interested in mathematical physics. Now, your question that whether quantum field theory is for physics, of course, because I will say, look at the example of Heisenberg. So let me tell you a story. You will find this story, for instance, in the functional analysis book by Peter Lux. So I think it's Friedrich, I might be mistaken. He is also famous functional analyst. So Friedrich met Heisenberg. So Heisenberg was almost end of his career. And so discussion, and at some point told that we operator theorists really want to show some gratitude to you, because unless you started quantum mechanics, as you have seen, none of this was forced to understand. Yeah, so we started to do it because of your work. And then he told this and this and this. And then at some point, he told, like, some mathematician called von Neumann, who actually developed much of the unbounded operators, really understood what is a self-adjoint operator that you will also understand after a while, and then everything else understood. And then Heisenberg asked this question, so what's the difference between a self-adjoint operator and a Hermitian operator? And the mathematician was really stunned, because he thought, Heisenberg, come on, he's the father of quantum mechanics, he must know. So maybe some of you do not know this thing, but you will see the difference. And I can share my personal history. So when I went my second master's, I went to my master's supervisor, and he gave me some paper, and then I have to work it out. And he worked really hard to prove something is Hermitian. I think if you are from physics, then you know this word better. And then I asked him, why you work so hard to prove this is self-adjoint? I mean, isn't it just clear from there? And then he told, you are those who do not know the difference between Hermitian operator and self-adjoint operators. So the moral of this story I take, Heisenberg didn't know the difference, at least at the beginning, but he discovered quantum mechanics he discovered it, not in a very proper, complete way. And he was not successful. He was one of the smartest physicists ever, at least to me and people around me. And he didn't start it like von Neumann. On the other hand, look at the trajectory of von Neumann. And I told you, both were postdoc in Göttingen. Okay? Heisenberg was a postdoc of Max Born. Von Neumann was a postdoc of David Hilbert. But von Neumann, he was not happy with this thing. He said, okay, I want to understand. And he was not even happy with Hilbert space formalism. And you will see it is not really sufficient to have Hilbert space formalism. So he developed basically what is now we call the operator theoretic approach of quantum mechanics. And it really gives lots of new mathematical ideas, lots of new mathematics actually emerges due to this physics, to understand physics. And then it also helps physicists to understand certain quantum phenomena. So come back to your question, I would say this is one thing, and mathematicians are approaching from one direction, physicists are approaching from another direction, but end of the day, we are doing the same thing. Sometimes this direction is useful, sometimes that direction is useful, but my viewpoint, I am just a young student like you, is that we need this both viewpoint to understand this thing. So it may happen some physicist will find a very interesting physical idea like Heisenberg or Einstein to understand quantum field theory for non-perturbative regime that we almost do not know anything. But he might lack of mathematical rigor, mathematical understanding. And then some mathematician like von Neumann will try to understand it, and then he will probably see that, wow, you have a whole new world of mathematics that we never knew before. Physics tells us to, go to this world, and now we discovered like this operator business. Or it can happen the other way around. Maybe this time mathematicians come first and physicists catch up later. This may also happen. Or it may happen something very different. So my viewpoint is that whether you do from more theoretical physics viewpoint or mathematical physics viewpoint, do what you like, but do what really you like. Not to take someone's side before you like something, before you know something. So if you don't like this operator theory language, you are most welcome. I don't have anything negative against you. But what I'm saying that at least look at the other side of the bridge. And it's like testing a new food, right? If you have never tested a food, how then you know this is not useful? And at least I shall try to convince you, mathematical way of understanding gives quite influential result in physics, not only mathematics, in physics also. That is not possible, or that has not been possible from physics way of thinking. And the other way is also true. Unless Heisenberg discovered it, probably mathematician will do it maybe after 50 years later, or who knows. So purpose of the philosophy of this course is to really talk between maths and physics in the context of quantum mechanics, and then you choose what suits you better, what you find more interesting, and go for it. Personally, I think both people has success, and probably this is a good way. Like, this is no unique way, this is the right, this is the wrong. Both are useful in their way, and then we have to combine. And historically, look, that's what happened, right? People were doing classical. Look at Newton's. So Newton wanted to understand very simple thing, like volume of an irregular shape, and he discovered calculus. But you say, oh, no, Newton didn't discover because Newton didn't know convergence and anything. That's true. And then you need people like Weierstrass who understand how to do it, and that basically gives rise of real analysis. So the whole field of real analysis started historically to understand calculus, and calculus is started because we understand some natural thing. So in this case, again, physics tells mathematician to look at some structure. And it is not the first time, it is not the last time. It's happening again and again. And sometimes the other way around. Like if you follow this operator algebraic framework, you can tell certain thing about entanglement structure of quantum physics that is not possible using this physics way of thinking. And then physicists are now appreciating this thing. Okay, if you know this operator algebraic classification, the so-called von Neumann algebra classification, then you can talk about entanglement entropy, and this sort of thing. And now they started learning of this language and some of the thing because they found it useful. So now you see there is also the other side. Sometimes mathematician can also give something to be interesting for physics. And there are many examples. It's quantum physics, quantum field theory, geometry, category theory, and whatnot. Okay, and maybe some of you will also contribute in this thing. So I really think that both people has to play a role, because end of the day, our aim is to understand nature, and we are using different tools or different routes to understand it. And unless one is succeeded, ultimately, we cannot say, oh, that's complete nonsense. Of course, we can say, like, if I do something which has no application in quantum mechanics, then I do not expect to understand something quantum. It may happen accidentally. But for instance, if you understand, there is also this path integral formalism of quantum physics. And if you want to understand that, and if you say, oh, I want to understand that, but I want to study operator theory, then this is not useful. Then you have to go to hard measured theoretic thing. Yes, and that's also very interesting. But you see, you have to at least some sort of relevant why it is useful or what you are doing. You have to know that. And then if you keep going, I believe you will get something. Again, if I do something very irrelevant to quantum physics, for instance, I studied my undergrad in engineering, and in engineering, there is something called digital electronics, where electrons are considered like classical ball. So they are in some energy state and next energy state, and the engineers call it 0 and 1. So when I first read it, I saw it's complete nonsense. Electron cannot be localized, blah, 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 all this quantum mechanics. But then I realized after a while that if you look at certain energy scale, then this is almost a classical thing, an electrical circuit. It works like this way, and it's a practical right way to understand thing. So then there is no problem. So at some point I was a bit unhappy about this way of thinking, but later I realized unless they thought this way, there will probably no electronic semiconductor revolution. Yeah, so they have their own achievement. Physicist has their own achievement, mathematical physicist has their own achievement, and everyone has their own achievement. But what we need to understand, or I think, that we need to know who is doing actually what, and then we decide where we want to fit ourselves. And it may happen that you are part of this and that's not a problem. But the whole thing is that at least you know what you want to do, where you are fitting in. Yeah. Yeah, so someone wrote like he's interested in condensed matter theory, and then he found interesting application, which is now quite a fascinating topic, this fusion categories thing, and he wants to sure that's the beauty. You find it interesting, and then you go in that direction, and then you keep going. And someone will maybe working on fusion category, he find, oh, that's a nice interesting application in condensed matter theory. Let's go there, and that's the exchange of ideas and viewpoints. So yeah, of course, feel free. Any other comments? Please feel free to share your opinion. I think that's also nice.